Hi, good morning, good afternoon, and good evening, everyone, depending on where you are watching us from. How are you, everyone?
Doing very well today, thank you.
Good.
Yeah, pretty good.
Nice, it's good to hear. It is a very exciting day today because we came back with another awesome session, which is, what is it going to be, Heini?
So today we're going to be talking about linear algebra. Very exciting topic.
Yeah, it is. Could you tell a bit more?
Yeah, sure. So linear algebra is kind of this method in mathematics that we're going to need whenever we go to these situations where we are working with multiple variables, multiple things that are changing, for example, in our mathematical algorithms and things like that. And it's used very widely in many places, even in things like neural networks and things like that, that we might not even think about, that it's kind of in the background there, doing all the work.
Nice. That's pretty exciting, actually.
Yes, it is.
Yeah, I couldn't wait for today's sessions because I think it is going to be a really interesting topic. And it is always nice to close the working day with a nice, relaxing mathematics session, right?
Yes, very relaxing.
As always.
Yes.
And then we should also say, as always, if you have any questions or any comments, you can just write to us in the chat.
Yes.
And welcome, everyone. I hope you'll enjoy today's sessions. Guys, shall we get started?
Yes, let's do it.
Hi again.
Hello.
So, how about telling us a few words about ourselves first? So, what is AI42? Håkan, can you tell us a bit about our motivation?
Yeah, so basically what we have found is that it can be difficult to find, a single resource where you can learn everything about artificial intelligence and you can start from scratch. So the main idea here behind AI42 is that we will give you a full introduction here, starting out with the mathematics and then continue on with, the statistics and probability theory, and then talk about the languages like Python and R and Scala, and then also talk about how can you set up machine learning pipeline, for example, and also have more advanced topics such as reinforcement learning, for example. And we want to provide this in one place, so that's why we started this AI42.
Yes, and AI42 is not just a cool place where you can learn stuff. We are going to provide you a lot of resources that you can use as a knowledge base when you want to get started in the field of data science of AI. And the concept is really simple. We would like to involve professionals to come from all around the world and tell us about their knowledge. And as Håkan mentioned, we will cover a lot of different topics. And every second week on Wednesday, we meet here with a new session that is helping you to build your career in data science of AI.
Yes, and maybe we should say a couple of words here about where you can reach us. So we are both available on social media, on Instagram and on Twitter and on Facebook, and we also have our own YouTube channel and our own meetup. So if you scan this QR code, you can get to our YouTube channel, and you can also sign up for our meetup to get notified about future events.
Yes, and additionally to learning a lot, from our streams and from our knowledge base, you will be able to connect with the best-in-class experts from all around the world that will also hold lectures and workshops with a lot of rich content at AI42.
Yeah, and then we should also thank our sponsors, who is sponsored here by Microsoft. And in addition, our intro music is composed and performed by Mina Marie, and all the graphic designs that you can see here in our stream is by Levente Pongor.
Yes, and as final words here, I would like to mention that we are in close collaboration with global AI community as well, which is why they are providing us a platform to stream our sessions as well. And we plan to collaborate with other organizations as well, which can give you a really good opportunity to broaden your network in the AI and data science communities.
Yes. So then I think we can get back here to Heini.
Yeah, and before doing so, let me mention it once again that feel free to ask questions from us in the chat, and we will answer them at the end of the session. I hope you will enjoy it. Have fun. Hi, welcome back, Heini.
Thank you so much.
I hope you feel good and you feel ready.
Yes, I am really excited about this one because it is one of those topics that can seem so abstract, but it's used so widely. So really looking forward to kind of digging into those details, how it all works.
Oh, me too. So maybe, Heini, if you're ready, then take it away.
Yes, let's do it. So all right, and welcome everyone to our third mathematics session of linear algebra here. And as we've been going through the previous parts, we've been looking into algebra and calculus and all those things. But we haven't considered the situations where we might have multiple variables that we're looking at. And that's really what linear algebra is replying to. So even when we think about this solution that we've been walking through, that we have our graph where we have multiple points, some measurements, for example, for our machine learning algorithms, and we're trying to fit the straight line in there. So how are we able to do this? We kind of got one part in our previous session, but we're still missing a bit of information to be able to understand what is happening. So just to give you a recap where we've been coming from. So we started with basic algebra, looking at things like sets of numbers and how to work with those sets, and just looking at equations and how to solve those equations, etc. After that, we went into calculus in our previous session, which mainly focused on derivatives and integrals. And so today we will be kind of taking the next step with linear algebra. After this session, we will also still have the statistics and also the probabilities sessions as well. So if you have not met me before, I'm Heini Ilmarinen, and I work as a DevOps consultant at Polar Squad. I'm also a Microsoft certified trainer, and my favorite topic kind of around what I do daily is the architecture side of cloud infrastructure and data things. But I am previously a math teacher, so this is kind of going back to my roots, and this is really something I enjoy as well. And I really like that I get to combine what I do now and what I used to do. And if you haven't noticed, I'm a bit of a serial doodler, and you'll see those pictures here on the slides as well. So in today's session, what we will be looking into within linear algebra is kind of the core question is what happens when we have multiple variables. And we will come across this situation in many places. And so we will start with an introduction to vectors and what vectors are. Then we will take a first step into solving sets of linear equations. But we will take a little break to look into matrices before we kind of finish off that part. And then we will continue with our solving in that case. Then we'll look at what are linear transformations. We will look at some qualities of matrices, like the identity matrix and the determinant. And then we're going to wrap up everything with kind of how do we actually use this. So with linear algebra, what is interesting, for example, when I was studying math, this was actually 2 full courses that consisted all the information regarding linear algebra. And so that means pretty much a half a year within university. And so it's a massive amount of information. And if you're just trying to find information on the internet about linear algebra, it can be kind of this vast swamp that you have to swim through and try to find the relevant information. And definitely you don't have to know every single detail to be able to do machine learning things with linear algebra, but it helps to understand kind of the transformations and how vectors and matrices work and all those kind of structural things and what happens to them. It really helps to understand that, especially if there's something weird happening with your algorithms, for example. Understanding what happens on the background really helps. So let's get started so we can get to the beef of what we're looking at today. So we're going to be starting with vectors. And so one way to describe vectors is to take, again, a coordinate system, which we've been working with in the previous session, and describe a vector as an arrow in that coordinate system that has some kind of direction and it has some kind of length. And let's just draw another one here as well. So right now we have 2 vectors drawn here, and both of these have what is called a magnitude and direction. And so the magnitude means what is the length of that vector, and the direction just means what way is it pointing to in this coordinate space. But there is also another way to mark vectors. And for example, to mark our vector A in this picture, we can take our A and mark it as 3, 2 in these brackets. Where does that come from? So if you look at this picture and at the vector A, you can get from kind of the starting point of that vector to its tip by going 3 steps right on the x-axis and then taking 2 steps up parallel to the y-axis. So you take 3 steps to the right and you go 2 steps up. On the other hand, this other vector that we have here, the B vector, this one you can get from the start point of the vector to the tip of the vector by taking first 1 step to the right and then taking 1 step down. So whenever we go into the kind of the opposite direction, we mark that with a minus sign number. So we get these two vectors that we have here. And in regards to machine learning and how you use vectors in machine learning, you most often work with this second notation. You normally don't have this visualization of vectors available to you, and you don't work with them in a visual way. So, but when we're trying to understand what happens with vectors, it is really useful to look at them in this graphical way because it helps us understand. And whatever we notice in this graphical way, then those will also apply just when you're working with numbers. So let's just, and when we're working with those numbers, we don't pay so much attention to the magnitude and direction. So let's just kind of take that out of the picture and just work with a graphical visualization and then just the bracket notation as well with the numbers. So as the first thing that we can do with these vectors, for example, is to add them together. So we can add together our vector A and our vector B. So that would mean that we're adding these vectors 3, 2, and 1, minus 1. But what actually happens when we're adding together these vectors? Well, what we want to do is take the second vector that we have, which is the B vector, take it out and move it where the A vector ends. So we kind of get these two different trajectories that we're taking with these two arrows. And so what happens then that the result of this addition is what goes from where the A vector starts to where the B vector ends. So we get a third vector, and that is the solution. And so if we again read it from the graphical interface, we can see that it is taking 4 steps to the right and going 1 step up. And we notice that it is taking the top numbers from our vectors, so the 3 and the 1, and adding those two together, and then taking the bottom numbers from our vectors, so kind of the direction into the y-axis, and adding those two together as well. And that adds up with 1. So we end up with a vector for 1. So in this way, we can put vectors together, we can add and subtract. And the nice thing is that if it works for these 2 dimensions, it will also work in multiple dimensions. But there's other kinds of kind of transformations that we can also do. So for example, we can multiply. So let's kind of return to the start situation here. We can multiply one of these vectors. And let's just for our case take the vector b and multiply that by 2. So it would be 2 times the vector 1 minus 1. What would that look like in our graphical presentation? Well, that would look like we take the b vector and draw another b vector after the b vector. So we kind of have 2 of these b vectors, one after the other, pointing in the same direction, kind of having that taking 1 step right and going 1 step down. We have the same vector that we're just putting one after the other. And so what happens here is we can actually take this this number 2 that we're multiplying with and multiply both numbers in this vector by that 2. And so that means that our end result ends up with a vector 2 minus 2. So seems really simple. Does it get any more difficult in situations where we, for example, have 3 dimensions or 4 dimensions? For example, in 3D, we can kind of imagine how those vectors go, but if we go to 4 numbers in one vector or 5 numbers in one vector, we can't really visualize that anymore in any way. But whatever we learned from this point, the nice thing is that these calculations are the same in multiple dimensions. So whatever we learned here, we can take whatever amount of numbers we have in one vector. So now you have a basic understanding of how vectors work. And next we're gonna look at solving a set of equations. Why? Because actually kind of the core problem within linear algebra when it's considered within mathematics is solving a set of linear equations. So we're gonna be looking at that next. And we're just going to have an example that has x equals y plus 5 and a 3x plus 2y equals 5. And one way to solve this equation would be, for example, to take these 2 equations, draw them out in a coordinate system, and just see where these lines cross. But if we have, for example, the z variable in there, we have maybe a 4th variable, and so forth, that doesn't work anymore. So we need to have some kind of other methods. And with this simple example, we're going to be looking at how to do this with linear algebra. How can you solve this equation? So first off, what we want to do is that we have all the terms that have variables in them on the left side of each of these equations. So for example, for the first one, we want to write that in the form x minus y equals 5. So we want to move the y to the other side of that equals sign. We want to transform it in that way. And after that, we are going to mark this equation in a matrix form, in a linear algebra kind of notation. And what that will look like is that you will have these brackets and you will take the values of numbers that multiply the x's and the y's and write them in the order that you have them here in the equation. So you will have the 1 and the 3 from in front of the x's. You will have the -1 and the 2 from in front of the y's. And then because we have the x and the y, we will have those as one vector. And then on the right side, we will have the solution to this equation set. So now we got this kind of vector-looking thing in the beginning, but it has 2 columns. So this is actually called a matrix. So we found the matrix finally. But let's kind of take a step back and look at what matrices are before we head there. So we have a matrix here that has 2 columns and 2 rows. So it is the exact same matrix we had in that equation. I just grabbed that one, and let's start working with that. So it has 2 rows and 2 columns. So it is called a 2x2 matrix. And the first 2 in this 2x2 notation is the number of rows, and the second 2 refers to the number of columns. So as we actually have a matrix that is a square matrix, so it means that there is an equal amount of rows and columns. We cannot kind of see the difference of which number refers to the rows and the columns, but the first number is always referring to the number of rows. So let's just grab this matrix that we have, and let's see how we can do multiplication with matrices. So I'm actually gonna grab the second part of our equation that we happen to have on the previous page, which was actually this vector xy. And you can think of a vector as also a 1-column matrix because it has just 1 column, but 2 rows. And so when we have this situation, we're actually able to do multiplication of the values in these matrices. And the one thing to note is that the amount of columns and the amount of rows in these 2 matrices that we're working with need to match, that we can do this multiplication. So how this works is that, let me grab my pen here. So how this works is that we take the first one here and we multiply the x with that one. So that will be our first step that we take. Then we take the -1 here and multiply the y with that one. So if we kind of take a look, we get that we have x minus y and 3x and 2y. So also here we take from the 3, we multiply by the x, and we take the 2 and multiply the y. So we kind of go through these different phases. We will get back to the matrix multiplication a little bit later and see kind of a more complex situation, how that works. So here we just kind of take each one of those, and the second numbers that we have, we multiply the y there, and with the first one, with the first numbers in the column, in the first column of the matrix, we multiply by the x. So that's what we get there. So pretty much if you look at this, this is equal to this equation pair that we had. So that's how we got from this pair of equations that we had to this matrix notation that we have, sorry, up here. Oh no, not quite yet. Up here. So this is how we got from this to the matrix notation. So we kind of went backwards a little bit. So now that we have a sense of, okay, matrices are this collection with rows and columns that have numbers in them, how can we use them now for solving this set of equations that we have here? So let's return to the situation where we ended up on our previous slide, where we left off. So this is where we left off. And let's just get a little more space for us to work with. So I am going to just grab the first matrix here that we have. And to solve this equation set that we have, we're going to use something called a method of elimination. And so what is going to happen is that we want to be able to make this that number there, the 3, we want to be able to make that into a 0. And somehow we need to make some kind of transformation to be able to do that. And so what we're going to do is that we're going to multiply the top row by 3 and then subtract it, subtract the top row from the bottom row. So we're transforming the bottom row, but we're using the first row to do that transformation. So what happens is, if we first take the very first number there, we have the 3, and we do 3 times 1 on the top row. So we do 3 times 1, and then we want to do -3, since we had a 3 in place of the 0. So that ends up being 0. But we also want to do that same thing to this second value that we have here in the matrix. So with both elements on the same row. And to do that, we again do the same thing. We do 3 times -3, which is -3. And we're going to do 2 minus 3 times -1, which ends up being a +3, since we have 2 negatives there. So we have 2 plus 3 equals 5. So that's how we get this second row that we have transformed so that we have a 0 there. But I actually have to get those out of the way because they're going to get in the way of our next step here. But remember, we had other parts to this set of matrix and vector notation that we had for this set of equations. So we still have the xy there, and we also had the 5 and the 5. But wait, we just did a transformation on the left side of the equation. And so that means we do need to do the same transformation on this right side as well. So really, we need to do the same thing. We need to do times 3 and then subtract. So what does that end up with? Whoops, that came a little too early. That's okay, let's leave it there. It will end up being, we take out the 5, and let's see what we're doing. We're doing 3 times 5 is 15, and then we want to do 5 minus 15, which is -10. So we're going to put a -10 in there instead. All right. And so what we've been doing here is what this notation that appeared on the left a little too early is doing, is that we're having a matrix A and a vector X that will result in B. So we've just solved this problem of AX equals B, where B is some kind of vector already, and the X vector is what we don't know. So we just solved our first set of linear equations using linear algebra. Pretty neat. So if we now kind of look at this situation, we have solved this equation. Well, wait, we are missing still the last steps, actually. So we have kind of simplified the equation. We have just 1 and -1 at the top, and then we have a 0 and a 5 at the bottom. And so what happens is, if we write this equation out now, kind of go backwards, back to the original notation, we have x minus y equals 5. And then we have actually 5y equals -10. So this is where we end up. And now we see that the bottom one is really easy to solve. We can kind of see that, well, y needs to be -2 because 5 times -2 equals 10. So we get y equals -2. And then we can take that -2 and put it into this top equation, which we have here. So we have x minus -2 equals 5. So remember, since it's 2 minuses, that is a plus. So x plus 2 is 5. So we're able to tell that x equals 3, because 3 plus 2 is 5. So we have solved x and y. And now we could even mark this in this way. So we have our x, y vector here, and this equals 3 and 2. And we have solved the equation. I almost got ahead of myself there a little bit. So we have now realized that the xy portion there is a vector 3, 2. So what is this matrix doing to this vector 3, 2 in this equation that we're looking at? This is kind of where we get to linear transformations, because actually the matrix that we have in the beginning there is doing a linear transformation on this vector 3, 2. So if we look at it closely, we have this matrix. We have the vector that we found the solution for, which is 3 minus 2. And we know that that ends up being 5, 5. And so what this matrix here is doing, it describes a linear transformation, how that vector changes. So if we kind of go back into the visual way of looking at this, we have our original vector, which is 3 minus 2. Again, we take 3 steps on the x-axis and 2 steps down. And that gets transformed. Oops, I want to go forwards, not backwards. There we go. Into a b vector, which is 5, 5. So it is 5 steps to the right and 5 steps upwards. So we see that this vector has changed. But now having this matrix here, we could put in another vector in there, something completely different than the 3, 2 that we have here. So if we, for example, we want to do the transformation that is described by this vector here, and we want to do this transformation, let's say, to a vector that is 1, 0. So what would that kind of vector look like here? So it would go 1 step to the right and no steps up. So it would be just right there along the x-axis. And then we need to figure out what is the solution, what happens. So to get that solution, we are going to do multiplication again. So we are going to multiply 1 times 1 plus minus 1 times 0. So you notice we did 1 times 1, again going to the x, and minus 1 times 0 going over there. And then as the second portion, I am going to do 3 times 1, and then 2 times 0. Plus 2 times 0. So what that ends up being, we just calculate. We have 1 plus 0 because there's a 0 multiplication there. So we get a 1 and a 3 because, again, we have a 0 there. That goes to 0. So we get a vector 1, 3. Okay, what does that look like? So let's just grab another color to be able to see that. So that's about where the tip is going to be, and that is where our arrow point will end up being. So we can see that our vector that we had along the x-axis gets kind of moved a little bit. And in this way, this was kind of the part that describes how the x side is always going to transform. So the x part of the transformation that we started with here this is how it will always transform, going into that direction, going up. And so we could also find out this transformation for many other vectors as well. And for example, look at how does the y component get transformed, etc. And for example, then those would help us understand how does this transformation work? How does it transform these vectors? And the thing is, they will always get transformed in the same type of way because it is a linear transformation. And so whenever we do that transformation, after that, whatever vectors we have started with, for example, the addition between those vectors needs to stay the same. So that still needs to hold. So this is how linear transformations work. So even though we started with this issue of solving a set of equations, which maybe isn't, well, it's related to machine learning as well, but a lot of times in machine learning, we do linear transformations. And that is what a matrix can represent. It can show us what a linear transformation does. So how will we then know what this linear transformation is actually doing? For that, we need something called the determinant. And, well, where is my slide? Sorry. So we need the determinant. So what the determinant is doing, this is a scalar value that describes properties of the linear transformation that the matrix is doing, that we're using. And based on the different kind of matrices we might have, the value of the determinant will vary. So for example, if we start with this specific example that we have been kind of using all along, if we stick with this one, oops, where is, there we go. So we've been having this matrix, which is 1, 3, and minus 1, 2. And whenever we calculate a determinant, so that cannot actually be an equal sign, we can mark it with these lines. So this is 1, 3, minus 1, 2. So that is what a determinant is. And so if we had given this matrix a name, for example, it's called A, then we can have determinant of A. So that's another way to tell people that, yeah, we're going to be calculating some determinants here. And so to calculate our determinant, there is kind of this equation that we can use that determines how you calculate that. So to calculate the determinant, we're kind of going to do this crisscross multiplication. So we're going to go across like this. And so whenever you have a 2x2 matrix, it is really easy to do this determinant calculation. And in some cases, it can be more difficult if you have, for example, a 3x3 matrix. Then you might have to kind of break it down into smaller pieces and go step by step using these 2x2 matrices to calculate it. But this is a really good place to start. So how this is calculated is that we do the 1 times 2. So we first do this direction, and then we minus the other direction that we have. 3 times minus 1. And for this one, we get 2 plus 5. No, 3. Sorry about that. And the end result is 5. I got ahead of myself here. So for this particular determinant, the end result is 5. But so for many just general matrices that we might use, it will be just some kind of random value. But for others, it can be, for example, a 0 or a 1. And depending on what that result says, it will tell certain things. So for example, if we look at something called an identity matrix. So identity matrix is a matrix that has values of 1 diagonally. So if we have a 2x2 matrix, it's going to have just 2 1 values. If we have a 3x3 matrix, we're going to have 3 number ones across diagonally, and all the other ones are going to be 0. Well, why is this matrix interesting? Well, it is interesting because when it is doing a transformation, if you use this matrix to do a transformation, it doesn't actually do anything. So it's an identity matrix. You can think of it as, for example, when we're doing addition, if you add a 0, it doesn't do anything to the number we started with. So it's like it's not transforming that number into anything else. So it's kind of similar in that way. And so if we look instead at the determinant of this one, so we're going to look at a kind of mixed notation here. Sorry about that. So we're going to do this. We're going to look at the determinant. And what we're going to do is, again, we're going to do 1 times 1 minus 0 times 0. And we end up with 1. So for any identity matrix, the determinant is 1. And that is the sign, if you find any kind of matrix, that is a sign that this doesn't do any kind of transformation. So it's kind of interesting to have these different kinds of signs telling you what each type of matrix will do in regards to transformations. There is also one kind of transformation that we can do to matrices, that is a transpose. And what a transpose does is it kind of flips the matrix. But what does that mean? What does it actually do? So what that does is that if we, again, we're going to stick with our favorite example here that we've been working through this whole session. So we're going to start with this matrix of 1 minus 1. And then we have 3 and 2. And we want to do a transpose. And what the transpose ends up doing is it takes a row and flips that into a column. So if we take the first row here, we take that, we flip it to a column. Oh no, heading backwards, just one step. 1 and a minus 1. And then we take the second row, and again, we'll flip that into a column. So we take the 3 first, and then the 2. So we were able to get the transpose. So the transpose kind of flips the matrix that we're working with. And for example, we could even be working with a matrix that has just 1 row. And we could even do the transpose on that one. And when we do the transpose, it turns into a kind of, we're again in a 1 column matrix situation. So we have some idea of what are vectors, and we have some idea about what are matrices, and how matrices can be used to represent a transformation that is done, for example, on a vector or on a matrix or something like that. So what do we use this for? That is kind of the $1 million question here. Like, why are we learning about all this stuff? So for example, one place where this is used is the least squares solution. And what this least squares solution does, as we were looking at solving that set of equations, and we had this AX equals B situation that we were able to solve. But what if there is no solution? So the least square solution is looking at what is the best approximate solution in that scenario. And so that is kind of the solution that we then find through this least squares problem. So how would this look in practice? Since we only have such a short time for this linear algebra walkthrough, I will kind of introduce the idea of what is the logic, but we will not be going into the details of how you actually calculate it. So you will just get the idea of what are kind of the points that you walk through to do and solve this problem. So we're gonna have a coordinate system here, and we're gonna have our set of data as points here. Let's just make it somewhat like you can imagine you can find a line there. And I'm gonna grab another color for our trying to fit the data into this one. So we're trying to get a nice straight line that is the best solution. That might not have actually been the best solution there, but that is kind of past the point here. So what we are interested in is how do we solve this using this matrix notation that we've been using. And if you're looking at this problem, yes, this is linear regression. This is what we're doing, kind of looking at this problem that we have. So each of the points that we have in this picture, we can describe them with, for example, just being a set of values, because it has some kind of value of x and it has some kind of value of y. So we have multiple of these points here. And so each one of those points has these coordinates for it. So we kind of have this situation where we're trying to fit this line through all these points that we have here. So I'm just going to take, let's say, 3 points from here, so we don't have to worry about kind of the summation aspect here, but let's just grab a third point there. So imagining that we have this third point, we want to find these estimators that will then minimize the mean squared error of the model. So how far is each of these points from the line? That is what we're trying to look for. This B that will tell us what is the closest point. And oftentimes we will also need some kind of a fitting what is the term? Oh my gosh. I mean, something that will then take care of kind of how are we fitting on the whole axis. I will try to come up with the word in just a second. But so essentially what our problem is here, we are trying to find a linear equation that will fit this kind of situation where we have our y's and then we have on the other side we have our x's. And then as the kind of what we're multiplying that with, there we have this estimator. So that is really telling us like how far is this from the line? How much far is each of the points from the line? So we're trying to find those estimators. And there's always going to be like one less than you have of the x values of x. So that is kind of the solution that we're trying to find there. And as you can see, since we have these multiple lines, and in this case, we have much more points than the 3 ones, so you get a much more complex environment as well. And so if we want to kind of write this in a more simple way, we can get to a notation of y equals x times b, where that b is also a vector. And if we were going to do kind of write those out, then we would be able to get a little more detail. But this is kind of the core problem that we're trying to solve with this one, to find the best estimator that will result in that line being the most optimal solution for this problem. So that is the goal for this particular one. So if you want to find more information, you can find amazing videos on YouTube. If you just look for least squares solutions for machine learning, you will definitely, there's really good explanations available for that if you want to go more into detail. This was more just introducing the idea because we are starting to run out of time here. But as kind of the last little bit that I want to give you before you head out is kind of a bit of a teaser as well about where is this used in machine learning. So I mentioned this a couple of times as we were going along here, but the other place that this is used a lot, for example, is image recognition. And for example, if you're doing neural networks. So you might kind of wonder, what do images even have to do with matrices or vectors or all that other stuff? What's the connection? So let's kind of take a look. I'm just going to draw a simple image because I'm going to do this hand-drawn and we don't want anything too messy here. So if you think of an image, you can think of that as this pixel grid. So I'm gonna draw a very low resolution picture with just a few pixels. So let's see, I'm trying to get my pen visible here again. So you can think of it as kind of this grid where your image is stored. This is just going to be a 10 by 10 image, or just because that's kind of fast-ish to draw. Okay, there's our 10 by 10 pixel grid, as you can see. And so any image that is drawn in this grid will have, for example, some kind of color. But I'm not going to use different colors, but just let's try to make a somewhat of a ball here. And based on how many pixels you have to use, it will be more or less of a ball, or resembling a ball-like structure. So that is kind of our image that is on that grid there. So what could be a way to even represent this? How does this relate to matrices? So how you can mark this is also as a matrix, where each one of these pixels that you have there is actually a number. So for example, the very first row would be just zeros. I'm not going to draw that all out, as well as the second one. But on the third row, we would have 2 zeros, 4 ones, and then zeros again. I'm simplifying this a little bit, but not too much. And then we kind of go along and we go through each of these rows. And unfortunately, I couldn't estimate how much space this would take. And in the situation where you have, for example, colors, or you have more darker tone of, for example, grays and blacks and things like that, you would then use not just zeros and ones, but just you would have a range of numbers that you represent those with in this matrix. So this matrix will also end up being a 10 by 10 matrix. So I only now drew kind of part of that, so we get the idea. So each of those pixels is represented by a number. So this is our data coming in. This is what we want to do image recognition on, for example. Then if we're using a neural network, what that neural network is doing, it is doing those transformations on this matrix that we were talking about today. Similar transformations, more complex scenario, but it is still based on those transformations that we were talking about with our very simple example today. So that is kind of your teaser for the end of the session. Yes, this is used in many, many places, and you can represent many things as matrices or vectors and things like that. And the transformations that you do on those then allow you, for example, to find shapes, to recognize cats and dogs, or whatever you might want to find from your images. And so this is really in the whole linear algebra is an essential part of machine learning and many topics within machine learning. So that's the last bit for today. Thank you very much for joining, and I really hope to see you in the next session as well. Thank you very much.
Wow. So this session was really, really hardcore. I mean, it was really exciting, and it was good to see how these things are connected together in the end, and that was really awesome to see. Heini, did you enjoy today's session?
Yes, I did. I really enjoyed it. Wish I could draw better on the fly with my last picture, but the point was to just understand the idea that is behind all this. Like, this seems like such an abstract idea, but it has so many use cases that it's almost like ridiculous how much it's used in places. So it's important to understand the basics and how everything works.
Yeah, we got a lot of cool comments actually during the session. For example, that thanks, this topic could have used another hour.
Yeah, exactly. That's how I felt.
But that's so true, right?
Yeah, definitely. Because I had to cut some corners and cut some topics out to just fit it in this hour. And I really just wanted to make sure we get to some of those like really important points of the transformations and things like that.
Can you like share some places where people could practice a bit more and get more in touch with matrices and vectors and transformations? Because I could see that they could follow us, but at the point of transformation it became a bit complex maybe for some.
Yes, I can imagine, because we did not have that much time, unfortunately. But what I can recommend it's kind of funny, I was recommended of this after one person saw my first session of this YouTube channel that I haven't seen before. So it's called 3 Blue, 1 Brown. I hope I got that right. And they have really good set of videos about both linear algebra and also, for example, neural networks. And so I would really recommend that. There they kind of take a little more time to walk through all these, and they have really cool computer-made animations about how the transformations work. So that would be kind of my go-to resource if you wanted to get more information and just follow along what happens.
Thank you, Heini. And also in the coming days, we should air our webpage finally of AI42, where we're going to share all the information that are shared also at these sessions. And there we are going to put up some links for you so you can go and practice these things that we talked about. if Heini is so nice to share with us.
Yes, I will do that. And I can definitely also make a few exercises for you guys if you would like to.
That would be really cool. Let me see if there are more questions. Oh, yeah. Well, you sort of talked about this, but let's go a bit closer. So could you give us more examples? So we talked about image recognition, image processing, and such. Are there any other examples to use when it comes to machine learning?
So for example, even like the image recognition is one part, but also speech recognition type of things. Then there's these topics in regards to the linear regression where it's used and solving that. So quite extensively. It's almost like where is it not used? Almost.
Yes. Yes, and also because it is used for other things, not just a simple machine learning scenario, but to calculate a lot of other things that are used during building a machine learning algorithm.
Yeah. So I can now see the question there. So how machine learning does linear transformation and connects it with the matrix. So it can be a little difficult to go to much detail here. So what it will, for example, as I showed the last example of having the image where you have these numbers representing each pixel, what happens is that when you're trying to tune the model, you're actually trying to find that transformation matrix and what will be the best possible solution. And so, for example, you might first need to do just a transformation on the picture that will make the edges of the image very recognizable. So you're kind of finding where are those big numbers and where are those very low numbers and where are the edges and just kind of picking out the edges. And then the transformation will, for example, then in the very end will end up with just, well, it's a cat or it's a dog. It's kind of hard to handle how does it get there. But for example, the first step could be just making those edges very visible. And then the second step would be kind of finding those defining points that make the difference between a cat and a dog. And of course, when you're training the model, that will kind of help you find the correct transformation matrices to do the job. And oftentimes, for example, in these neural networks, there is kind of many layers of transformations. So it's not just one transformation that we're doing, but we're actually doing multiple in a row.
Okay, thank you, Heini. And I also want to say thank you, everyone, for joining us. And thank you for the nice comments and the great questions we got. And feel free to ask us questions outside of the stream as well. You can follow us on Twitter, Facebook, and Instagram as well. And you can rewatch this session on YouTube if you go to the AI42 YouTube channel. Heini, could you give us a bit of a few words, what is coming next?
Yes, so we have 2 more mathematics sessions left. We've kind of gone in an interesting order because it might feel a little lighter after this session, actually, because we're going into statistics and probabilities. And a lot of times that is not quite as abstract as the linear algebra part. So it's a little more hands-on, and let's see what the data is telling us and kind of understanding those, for example, things like averages and what you can make from those, how can you actually use those, and then more complex statistical methods that we have to use.
That's also really cool because that's going to be some data analytics and
exactly.
Yeah, we are actually closer and closer to become data scientists in the end.
Exactly.
So I really hope everyone enjoyed today, and don't forget to follow us on Twitter, Facebook, and Instagram, and join us at our next session that is going to be in 2 weeks, which is the 24th of February, where Heini is coming back with another awesome mathematics session. Thank you very much, everyone.
Thank you, everyone.
Thank you
Take
so
care.
much.